Howdy, howdy, this is Mr. Potter. Today we're going to continue talking about polynomial functions and power functions. We're going to be talking primarily about graphing and some of the properties of the graphs of polynomial functions. So I want to start with the idea of continuity because whenever we're dealing with polynomials, remember that polynomials have a domain from negative infinity to infinity. It's defined for every value because every value between negative infinity and positive infinity can be substituted into a polynomial. We can multiply, we can add, and we can subtract. So every single point is going to exist, and every point between every other 2 points has to exist. So every polynomial is continuous on the domain from negative infinity to infinity. Now, you may be familiar with other functions like the reciprocal function, which has an asymptote. You may be familiar with some functions that actually have holes in them. But polynomials will never have any holes. Polynomials will always be continuous. And polynomials are always smooth. And this really is a calculus concept, but the idea behind smooth is that I'm going to have no corners and no cusps. Now, when I talk about a corner, of course, you're used to the y equals absolute value of x, which clearly has a corner on it. And if I was to look at a function like y equals 1 over, what am I trying to think of? What's a good function that has a cusp on it? I can think of y equals maybe x to the 2/3 power, which is going to be a function that's going to be like this. So functions like this that have this basic curve to it or these corners to it, those are not considered smooth because they have kinks in them. They have corners. They have sharp edges on them. All polynomials, anything that's in a polynomial form, one of the power functions that we talked about in our previous video, those are always going to be smooth. So let's take a look at an example of y equals x to the 7th minus 4x to the 5th plus 3x cubed. If I was to take a look at a function like that, hey, here it is already written out. I can factor this out because I notice that I have an x cubed factor in common with all of these. That's going to leave me with x to the 4th minus 4x squared plus 3. And this is going to simplify to x cubed, and this is going to be x squared minus 1 and x squared minus 3. So here I know that x equals 0 is going to be a solution, x equals 1 or x equals negative 1 is going to be a solution to this term, and x equals radical 3 or negative radical 3, those are going to be the solutions to this term. So I have 5 different roots, and we've also talked about multiplicity as well. This has multiplicity of 3, but that's okay because it's odd. This is going to be one of those where it's actually going to pass through the root, not bounce like we were used to. So each one of these have multiplicity 1, which of course means they're just going to pass through. Of course, I don't know if they're going to pass above or pass below, but if I were to actually graph these, well, let's see. I know that I have a solution here at 0, I have a solution at 1 and at negative 1, and I have a solution at root 3 and negative root 3. I also know the end behavior function because it's odd means that it's going to go down at negative infinity and up at positive infinity. So that means my graph has to kind of shoot down to negative infinity, and it's going to have to come up but then come back down in order to hit this because it is continuous. I'm not going to have any breaks, no asymptotes. It's going to have to follow through. And similarly, it's going to have to follow through here. It's going to have to follow through here. And it's going to have to follow through here. And this gets me the expected behavior. So this is a sketch of what my graph is going to look like. Keep in mind that my end behavior and my multiplicity is going to determine the shape of my graph. They're essential to understanding the graphs of the function. What I really want to talk about in this video is I really want to talk about extrema, or turning points, because keep in mind that when my graph turns, when it's going uphill, then all of a sudden it's going downhill, this point is my turning point, but it's also what we call a local maximum or a relative maximum, because it's the highest point on any interval that includes that point. Similarly, if I'm going downhill and then all of a sudden I turn and I go uphill, this point at which I stop going downhill and start going uphill, this is a local min. So the idea here is that we have extrema, a local extrema, is a point where the graph, or the function, transitions from increasing to decreasing, or vice versa. So in other words, whenever I transition from being an uphill function to a downhill function, that's going to give me a local extrema, a local maximum, a relative max. Similarly, if I ever transition from going downhill to going uphill, that's going to give me a local minimum, or a local thing. And there's going to be a certain number of these, just like there can be a certain number of roots. So the maximum number of extrema is one less than the degree of the polynomial. And this kind of makes sense, because if I'm used to something like y equals quadratic, then I know that I'm going to see a graph that goes down and goes up, and so I'm going to have one extrema. I know that cubic functions are going to go up, then down, then up. And so a cubic function, a function that's a third degree polynomial, is going to have two extrema. A fifth degree polynomial, if I were to have something like y equals x to the fifth plus stuff, well, I know that that graph has got to go up, down, up, down, up. Again, remember, I can have up to 5 solutions, 5 roots, 5 x-intercepts, but I'm always going to have one fewer extrema. Now, keep in mind that this is telling me the maximum number. Of course, I could have fewer. So I can always go up to 1 less than the degree, but if I look at y equals x squared, well, I know that y equals x squared is a parabola, and it's going to have 1. But if I look at y equals x to the fourth, just the x to the fourth, the quartic function, I know that that function looks like a wider-based parabola. But I still only have one extrema. And if I look at y equals x cubed, the actual cubic function, our cubic parent function, keep in mind that that function increases forever. It never actually has a place where it transitions, and so this has no extrema. So realize that there is a maximum, but there also is a minimum number of extrema that we could have. In the case of an odd function, and odd functions may have no extrema. And that's just by the nature of its end behaviors. The thing that I can go from negative infinity to positive infinity, it is entirely possible that I will be increasing all the way. But an even valued function has to have some type of transition, because it's either positive to positive or negative to negative. So an even function must have one extrema. An even function must have one extrema. It's either going to be a maximum or it's going to be a minimum, but we have to have one function, that one value that's an extreme value when we're dealing with even polynomials. So let's talk about this from the idea of Okay, I know what an x-intercept is, and I know how to find roots, and I know how to find increasing and decreasing. So let's take a look at y equals x squared times x minus 4 times x plus 2 cubed. So first thing I need to do is I need to identify my intercepts. So for my intercepts, keep in mind that I have a y-intercept and I have x-intercepts. The y-intercept is really what happens when x equals 0. So if I substitute x equals 0 in here, I'm going to have y equals 0 squared times 0 minus 4 times 0 plus 2 cubed. So that's going to be 0 times negative 4 times 8. So that's going to be 32. Well, no, 0 times anything is 0. Let's be real here. So I know it's got to be the point 0, 0. This has got to be one of my points. But if I look at x-intercepts, I want to know where each of these terms are equal to 0. So either x equals 0, or x equals 4, or x equals negative 2. But again, remember, it's not just what the values are, but we also need the multiplicity. Notice this x squared equals 0 has a multiplicity of 2, which means this has to be a bounce. Whereas both of these have multiplicities that are odd, a multiplicity of 1 or a multiplicity of 3, and so these are going to end up passing through that point, whichever one it is. So we've identified our solutions, our roots. And I know that I have to have a root at 0 and at 4 and at negative 2. So there's one at 0, one at 4, and one at negative 2. The second thing I need to do is I need to look at my end behavior. And this is a second-degree polynomial, third-degree polynomial, sixth-degree polynomial. Because it's sixth degree, it's even. So it's going to be either up, up, or down, down. But it's going to be the same, both up or both down. And my lead coefficient is 1 times 1 times 1, which is positive, so it's going to be the up, up. So I know that my graph does this and does this. And the third thing I need to do is I need to identify where local extrema may occur. So looking at this, I know that I'm supposed to go down to this point x equals negative 2, and because it's a multiplicity of 1, it's going to be passing through. And I've got to somehow get to this point over here, so that means somewhere between negative 2 and 0, I'm going to have a local minimum. Now at 0, my multiplicity is 2. That's a bounce, which means I actually have a local maximum at x equals 0. But somehow between 0 and 4, I have to get back to the axis. So somewhere between 0 and 4, I have to have another relative minimum. And then this is an odd multiplicity, so I have to pass through here. So I'm looking at this. I know that I have x-intercepts. I know I have solutions at x equals 0, at x equals 4, and x equals negative 2. I know I have a y-intercept at 0, but I also know that I have to have a local max at the point 0, 0. And I have local, horrible, horrible, horrible handwriting. Let's fix that. Oops. Local max at 0, 0, and a local min between, so somewhere in the interval from negative 2 to 0, and between 0 and 4. Now, at this point, I really can't get any more specific than that. I know that it has to be a transition point somewhere in between because I have to be decreasing here and I have to get to the bounce. Similarly, I have to get decreasing here and I have to get back to the pass-through. So I have to have some transition point between 0 and 4. And that's really the best that I can do at this point. But at least I can identify where extrema may occur. So, last thing that I want to talk about in today's video is I want to talk about the intermediate value theorem. The idea behind the intermediate value theorem is if f is continuous on the interval a, b, and f of a and f of b have opposite signs, then there must be a c where a is less than c is less than b, where f of c equals 0. In other words, if I know that my function is continuous, and I know that I go from a place below the x-axis to a place above the x-axis, then I have to have crossed the x-axis. Or similarly, if I started off above the x-axis, if my point over here is above the x-axis, and then I've got a point that's below the x-axis, in order to get from here to here, I have to have somehow, somewhere, pass through to get from point A to point B. That's the gist of the intermediate value theorem. At some point, I have to make that transition from being a positive function to being a negative function. So let's do one example of that. So let's say I've got this polynomial, and for convenience sake, I've actually substituted some x values to get the y values here. And what I notice is that to get from -2 to -1, there's a transition from being positive to being negative. And that means somewhere between -2 and -1, there's a solution. So we have a solution between -2 and -1. Somewhere in between here, the graph's got to cross the x-axis between -2 and -1, because I had to get from 11 to a -1. Similarly, because I had to get from a -1 to a 9, we have to have a solution between -1 and 0. Now the thing is, from a 9 to an 11, they're both positive. Maybe I dipped below the x-axis, maybe I didn't. I don't know enough for sure to say absolutely, yes, I've got a 0 between those. But I do know that between 11 and -1, those are a change in sign. So somewhere between 1 and 2, I had to have hit 0. So solution between x equals 1 and x equals 2. And similarly, this is negative, so I don't know if a transition happened here, but this is positive. From -9 to +29, there had to be another transition, a solution between x equals 3 and x equals 4. And by the way, this is a 4th degree polynomial, which means I can have no more than 4 solutions. Which means these are all of my solutions. I can't have any more solutions. And so I know that I do not have a place between 0 and 1 where my graph transitions, where it dips below 9 down to a negative value and then comes back. I know there's no place between 2 and 3 where from a -1 to a -9 it dips up above the x-axis and then comes back down. These are my only 4 solutions. And the intermediate value theorem helps me to figure that out. Remember that I'm looking for a transition from positive to negative or vice versa. And as long as my function is continuous, and every polynomial function is continuous, then the intermediate value theorem tells me I'll find a solution there. Once again, this is Mr. Potter. Thank you for watching. Have a great day.